Good evening, everybody, and thank you for joining us for this Cafe Sci. My name is Dan Lavoie, and I'm honored to be your presenter and host tonight. Cafe Sci is also supported by PPG. Cafe Sci is also supported by the fine people like you. The most helpful thing that you can do is invite your friends and family to join us here on Cafe Sci. Cafe Sci takes place the first Monday of every month, and you can find that speaker at CaymanScienceCenter.org. Before I introduce tonight's speaker, I'd like to remind everyone that you can ask questions by asking in the Q&A section on our live stream, or you can ask by raising your hand during the Q&A section, and I'll come around and get your question. It's my pleasure tonight to introduce Dr. Jeremiah Jamrom. Received his PhD in chemistry with a focus on isotopes-enabled metrology at Duquesne University in 2022. There, he researched small organic molecule quantitation utilizing dried blood cards as a matrix and quantitation of analysis below the lower limit of quantitation. Since then, he worked on Applied Isotope Technology, developing biomarker quantification suites for human health applications. That was a lot, but I hope you all really enjoy it. And furthermore, I give you Jeremiah.
Oh, good call. Don't want to amplify me twice. Once is plenty. Hey, so I do want to thank everyone for coming out on this very cold day. And I also am going to apologize slightly. My eyes aren't as young as they used to be, and so I might strain to look at some of the slides. But I do apologize for that, but here we go. As said, my name is Dr. Jeremiah Jamrom. I'm going to talk a little bit about quantitation, as I wrote too many times in my intro. And specifically, this is unique solutions to difficult analytes. So for traditional quantitation, we're looking at calibration curves. This is the gold standard of everything we use. And it's the gold standard because it's honestly pretty good. It works really well for most things we're going to do, but it tends to break down in certain places. And that's really what my research in grad school and also out of grad school has focused on. Independent measurements that don't use calibration curves but are accurate in quantitation. So we're going to look at a couple of examples, and then we're going to look at some results I had both at grad school and out of grad school. And if you guys are interested, I have questions after, so here we go. So I focus on mass spectrometers. There are 6 types of mass spectrometers, and this is just the spectrometer itself, right? There are plenty of chromatography or ionization protocols you could say is a hybrid, but there's really just 6 types of mass spectrometers. The quadrupole, which is by far the most widely used. If anybody here is in research using spectrometers, that's probably what they use. There's time of flight mass spectrometers, which are very, very good for proteomics and things like that, because it allows great separation between very small mass units. So it's really great for that. We're talking about Thermo Fisher, things like Orbitraps, things like that are part of time of flights. They're the second most widely used. Then we get more obscure. So magnetic sectors are, they're very high precision, but they're very expensive. So people only use them when they really need to. There's electrostatic sector mass spectrometers, which separate an entirely different way. They use electric fields rather than magnetic fields, but really they're mostly used in space. So if you guys are thinking about going to NASA and trying to use mass spectrometry, you might want to look into this one. There's quadrupole ion trap mass spectrometers, which uses a quadrupole, but it is able to get small concentrations and kind of stack them up. So it really is more efficient when looking at very small quantifications of things. And then there's ion cyclonic resonances, which is for medical research, but I have never really seen anybody use it. But that doesn't mean it doesn't exist. But we're going to talk a little bit about those, but we have to talk about specifically the quadrupole is what we're looking at. So the inventor of the quadrupole, Wolfgang Paul, he invented it with his grad student, Helmut, see, I can't even pronounce it. Steinvettel, thank you. And right here we have Wolfgang, and I was unable to find a picture of Helmut, and he won a Nobel Prize. So it pays to be the lead researcher and not a grad student, So we can find that. But so quadrupoles are very simple. Well, they're very complex, but they're very simple when it's boiled down. There are 4 parallel cylindrical rods that run, right? And on one side we have AC current, and the other side we have radio frequency controlled current. DC current and radio controlled current. The DC current moves things along, and then the radio frequency controlled current uses discrete mass integers that are based on the mass to charge ratio, M to Z, that only allow a certain mass of a certain ion to pass through at a time. All things are, other than that mass in that sector are pushed out then to either the quadrupole or the vacuum and removed. So we're really looking just at the mass we're looking at. There's some interference, of course, but what we're really looking at is just what we're looking at, and that's very impressive and very good because we can tell more or less if something is 166.1 or 166.3 mass units, which is might seem inconsequential and myopic, and in many ways it is, but it allows for vast swaths of information. We can differentiate between 2 molecules based on if one has a sulfur ion on it, or sulfur's 26, or 213s, which I can't remember off the top of my head right now. But we're able to differentiate between these 2 things. And so one of the things we were looking at is using what is known as an internal standard, a isotopically enriched molecule of analyte that we're looking at, and fitting them in those unique mass units. Because we know what is in there, we're able to use this specific part of a mass spectrometer to get very intricate and small measurements that are very accurate and precise. Now, in case there's any researchers in the audience thinking about using this instead of calibration curves, you're going to have a lot of hiccups, mostly because of government methods. They really like you to use how they like to be used. So this is not, as of yet, a substitute for any EPA or FDA or any other methods. You're still going to have to use the calibration curves and QC samples that they recommend because they are in charge and you got to do what they say, or you won't get CLIA certification. But I digress. We're going to move on a little bit. So one of the main reasons we're looking at, we'll be speaking of isotope dilution mass spectrometry instead of calibration curves, because there are a significant number of errors, biases, and imprecisions in calibration curves. There are 26 of them, I believe, and then all but 3 are taken account of by isotope dilution mass spectrometry. So it does allow you to be much more accurate. So there are things that you use calibration curves for every day that it doesn't matter, because these are all small things, but small things add up over time. And if you're looking at very small concentrations or very small wiggle rooms of what you're looking for, it can get buried. Some things, like I know zinc-copper ratio, if you're looking at that in blood, zinc-copper ratio is often very important. And calibration curves tend to bias them both, zinc and copper, but they're biased in the same direction, so it kind of cancels out. And a lot of the medicine we have is based on calibration curves, so you're still fine to use them, because even if they're imprecise, that's what all we have is based on. So you gotta have to kind of rewrite from the ground up if you're gonna do everything. But we're going to talk a little bit about isotope dilution mass spectrometry. This is the equation I use. It looks complex. It is not that complex, because you know most of the things here, which is great. It's great when you don't have more than one unknown in an equation. It gets real weird when you do. So, oh, nope, okay, good, great. Messed that up and it went right back. Thanks. So we're looking at the different concentrations of things. For this one, it was based on some of my work in grad school, so we're looking at methylmalonic acid. That's when I was doing this first part. I was using it again later, and we'll talk about that, but just because I was familiar with it, I didn't want to mess around learning new things. But we're looking for the concentration of the unknown, and we have a spike, right? And we know the concentration of the spike we're adding because we've measured it, we've added it. We know the weight of the spike because we've added it. We know the weight of the sample because we've added it. We know the abundance of the isotopes, both heavy and light. So in this case, carbon-12 and carbon-13. These are constants, right? So in nature, carbon-12, 99%, carbon-13, about 1%, carbon-14, 0.01%, but we don't really worry about that. And then the isotope in the spike, you also know because you make it. So you buy a sample online or a standard online, and hopefully it's NIST traceable. That's very good. But if not, you can measure the abundance of it. You know the abundance of the spike, so you know all that. So the only thing we really need to know is the ratio of carbon-12 to 13, which is what you're going to measure. So you get this number directly off the mass spectrometer. These are the values of the mass spectrometer, just the areas under the curve. You plug it into the equation, and it works pretty well. It's a single point calibration curve. And it works well because you know, you're just looking at a ratio of isotopes, right? So we're looking at the natural and the unnatural, the spike we've added, and there's a correction factor in there. So we're able to tell. So methylmalonic acid, this is just a little bit about this. It's an odd chain fatty acid. It's caused by, buildup is caused by cobalamin, vitamin B12 deficiency. It is the way we measure vitamin B12. It's inversely proportional. There's some mitochondrial enzyme deficiencies that can cause a buildup, and it is deadly, especially for infants. It's one of the reasons we test. It's a normally very qualitative test. You just test with a heel stick, and if it's elevated, that's bad, and we try some things to fix it. But at low concentrations, it might not show up on this test, and there is some evidence that small things build up over time, right? And it might be, impactful later. As I said, you just measure B12 levels. So I'm just going to show a little bit about the biochemistry in case anybody really cares about biochemistry. So it's propanol-CoA with a carboxylase. It becomes D-methylmalonyl-CoA, and then with an epimerase, it becomes L-methylmalonyl-CoA, and then with cobalamin and methylmalonyl-CoA mutase, it becomes succinyl-CoA, which then goes off to the citric acid cycle, breaks down just as normal. But if we have some issues, it won't, and it'll build up as methylmalonic acid, which can cause methylmalonic acidemia. It is deadly at high concentrations. So that's why we wanted to measure this, and so we did. So for this experiment, we used a fully automated blood card system developed by Gerstel Technologies. It worked, kind of. It wasn't ideal. It was pretty expensive, and it had a lot of issues and errors. But when it worked pretty well. It took the card, blood card, put it in a slot, automatically clamped it, moved it, desorbed blood off of it, put everything onto a cartridge, desorbed it off of a cartridge, and sent it directly to your LCMS system. And with that, we were able to get enough to quantitate. And we wanted to test this versus other analog techniques, right? So we desorbed, in addition to that, we desorbed off of blood card by punching with a 6mm punch, cutting it and either sonicating it and then speed vacuuming it, or putting it in a vortex genie and then speed vacuuming it. And we were able to get pretty, we were just trying to see which one would work best, and we were getting pretty uniform quantitation correctly on this. So for IDMS versus calibration curves, we were able to get a comparable data set looking at calibration curves, but the difference is the time, which in a lab is a thing that we all know and love. It takes so much more time. So for the calibration curve, for just a simple 6-point calibration curve, 3 QC standards, and a sample, it took 16 to 32 hours of runtime on the machine. Because you have to bookend calibration curves. There's a lot of very repetitive and redundant things based on EPA methods, which, good, we need to make sure we actually know what we're looking at. I'm not, blaming anyone or thinking that it's wrong. But with the IDMS, I was able to take it down to 2 hours, which much better. If you're looking at instrument time, is the big cost in a lab, essentially, right? You can only run as many samples as you can in a day, and with this one, you're able to cut it down greatly, which is great. There's just some of the results we had. Just very much better. So the error with IDMS is much better. Calibration curves, you see it maybe 58% error on some of the QC standards, and with calibration curves, no more than 8. So it is much more accurate and much more precise, especially at low concentrations, which is where we wanted to push things. Here's just a graphical representation. Sometimes it's easier to look at graphs and say, oh yeah, than numbers. Oh yeah. Okay, so that is one way how to do things to make things go faster. There's another problem with quantitation. Sometimes your analyte is not helpful. They can be very tricky. They can break down in instrumentation. They can break down during sample prep. For one analyte, we were testing an analyte that was curcuminoids. I don't know if anybody adds curcumin to any of their shakes or something. It's purported to do so many things it makes me suspicious. But, whatever. But we were tasked to analyze curcuminoids in blood samples. So what we had gotten was some blood samples that a doctor had dosed patients with, and he wanted to see if it had absorbed. Curcumin is awful to study. One, it breaks down in any light other than yellow light. So I worked under an LED yellow light in a walk-in fridge because it also is very thermally labile. And it is very unstable, so everything had to go very quickly. And that taught me I did not want to do that anymore. It was a nightmare. But it does break down fairly readily. And so when things change from the start of your sample prep to the end, that can be a huge issue. One of the ways that can be done is SIDMS, or speciated isotope dilution mass spectrometry. So for this example, GSHG, this is how it works. So we add, the species, GSH or GSSG, and you have those isotopically distinct. Then you add the spike, which is also isotopically distinct. And you equilibrate them, and some change. But because you know what you added, you can watch them shift and know what you added because you know the concentration of what you added. You know the mass of what you added. So it doesn't matter if it shifts mid-measurement because you know what you started with and you can track it as it changes. And there's a lot of, so you can measure it and it'll deconvolute it just right out in the equation. This is a challenging equation. I don't recommend doing it by hand, but Excel works pretty well with it. So for this was GSH, but we are going to look at some mercury speciation. Mercury also a big problem, right? You can look at mercury as it shifts, but there are 3 mercury species: methyl, ethyl, and inorganic mercury. So we can take these samples, we know what we spiked, and we have a different isotope for each spike. Mercury, thankfully, has more than 4 isotopes. So we know which one is which, and we can track them. So if we know that something is supposed to come out to 199, and then it comes up at 201, we can see it switched from methyl to ethyl. It's really neat stuff, and it's great for challenging little molecules that break apart. We've done this for many things in our lab, GSH, GSSG. I'm going to talk a little bit about mercury. We've also done with chromium for dietary sample companies. They were concerned that there was a difference between the chromium-3 and chromium-6 that they use. So chromium-3, as you all know, really important, one of the most important things in your body. You need it for sugar breakdown. Chromium-6, one of the most toxic things on the planet. All right, that's Aaron Brockovich was mercury, or chromium-6. And you have to be able to track and prove that if you have a vitamin supplement, you're not just poisoning people, which, you know, I think is good. I think that's solid science. I mean, that's what we should be there for, not poisoning people. For this, we were looking at small concentrations of chromium of mercury for a project in Canada. There is a project they're going to be mining for ores, and we wanted to make sure before and after that there hadn't been any contamination performed in the site, right? One of the few times that somebody had said to industry, well, we should probably measure beforehand so we know what's there, so that in case there's anything, we know it's your problem to clean up. So we worked for that. But as you can see, these equations are complicated. And this is only for 2. We can really go as many as there are isotopic samples. In theory, SIDMS can be used in multiple steps in sample prep to see where contamination is coming from. So if you see there's a lot of movement in one part, you can streamline it in that way. But we were able to get the 3 species out. Oh no, I messed up. This is the pointer, okay. We were able to get the 3 species out, and we were able to see a crossover for each species. So that was these measurements that might not come out as great here. But we were able to prove the changing of mercury as we were measuring it, which is great. Normally it was methyl or ethyl groups falling off, but also inorganic did switch. Here's some raw data of it. So it's looking at certified values and samples. So again, N of 4, 3 replicates of 12, just to get a 95% confidence interval, because we also want to be sure we're seeing what we're seeing. So for this, we use an IC chromatography system, which is a good way to do them because it's just based on charge at this point, but that's okay. All right, so we also at this point looked at hair samples of mercury, looking to see if we could see, and luckily there is a NIST certified sample, so we were able to test off that, and we were able to quantitate mercury, both inorganic methyl and total mercury in these samples as well. So the next part I'm going to talk about is kind of the newest thing that I've been working on. It's a different variant of IDMS, it's TH-IDMS. And for this, it boosts, we're looking at signal boosting and also specificity. So part of my doctorate, and then part of what I've been working on after, has been looking at getting right answers below the lower limit of quantitation, which is real difficult because it's a lower limit of quantitation. You can't quantitate lower than that. And you know, if you've done enough chemistry, you know it's 3.3 times the standard deviation of the calibration curve. But that is for calibration curves. IDMS has been used, it was developed for the Manhattan Project. I'm not, you know, saying one way or the other how I feel about nuclear weapons, but it is a good mathematical system, but no lower limit has ever been defined. In theory, if you can see both peaks of the isotope and the natural, you should be able to quantitate it. And so this is it's based on that, and also based on standard addition, essentially, which we all know about. Part of this is the error propagation factor. So for IDMS, there are these curves that have been worked out that shows the optimal enrichment. So for carbon-13, 98.53% is optimal. It lands right here at the bottom of this curve. But you can see the curve is pretty shallow, and you have some room to play with. So if you don't get 98.3, that's fine. So you can switch this. Maybe instead of 98.3, maybe it's 70%, maybe 65. You can boost the natural signal with that, with the other, 30, 40%. You can boost the signal and still get accurate quantitation. Not as accurate as at 98.53%, but accurate and below the limit of quantitation, so lower than you thought. And we actually were able to get a patent on this idea. So look at that. Capitalism. So there are some differences, right? But it's just these two numbers specifically. Everything else is the same. And these numbers, these abundances, they change and you measure them, but you have these to begin with, so you plug it into the equation, it gives you the same answer. So I can look at a little bit about, so there's no literature about changing isotopic ratios. This is post-modification. So if you've done work in chemistry, you buy an internal standard, you find out what you need to add, and as little as possible, because it's not inexpensive. You add it, and then that's fine. You get that. Naturalize your calibration curve off of that. But very few people, if anyone, has thought to change that spike that they've had because it is expensive, and if you change it, you could ruin it. But it creates a unique isotopic spike that you can add. It's meant to address optimization of quantification, and you can add the natural to amplify the sample. So here we have, I was doing lower limit of quantitation of methylmalonic acid. So calibration curves. I started and looking at the signal to noise ratio, right? Because once it's above a certain signal to noise ratio, you can't see it. You're trying to get a lower signal to noise ratio. And I was looking at the IDMS, lower limit of quantification. And after, this was the cutoff for the calibration curve because that's how the lower limit of quantification is defined. So we can't say under any of these that we accurately quantitated, no matter how accurate it is, just based on calibration curves. But because that doesn't exist with IDMS, and in this case TH-IDMS, we were able to push it lower. So we were able to accurately quantitate here, and it kind of dropped off here. But so it is, an order of magnitude better. So when we're looking at methylmalonic acid calibration curve data, we able to get this. We calculated it down, and with 95% confidence level here, plotted it, and these were the associated errors. So you can see that pretty bad. And even the ones that were worse had overlapped in the 95% confidence interval. If you plot them all out, there's no statistical difference between these. Because the 95% confidence of all of them overlap, they're all the same, essentially. Which makes sense, because it's all below the limit of calibration curve. We can't calculate this. But with TH-IDMS, we can. So again, the associated error, much lower. It does kind of go off the charts here. We couldn't say that this was very useful. But all of them, 95% confidence overlapped, and were discrete. Again, until this lower limit. So we were able to push the quantitation from 1.9, essentially, all the way down to 0.88, or I guess 0.28. So that is, what, 1.5 fold increase in quantitation, we can confidently say that we know what we're looking at down here, but we couldn't up here, which, you know, that's pretty great, especially if you're looking for very small concentrations of things, which is really important for proteomics, endocrine systems, mostly things in the human body that are produced at very, very low levels. We should be able to get it, quantitate it, and push it down. It's also very good for blood spots because you have much less to work with. So with a phlebotomic blood draw, you can have up to maybe 10 mils if you're lucky enough. I was never lucky enough, but if you're a real lab, you can get that. And with a finger stick, it's 10, 20 microliters somewhere in there. So you're losing a lot in what sample you have, and this helps us get back some of that. So TH stands for Thor's hammer. My PI at the time named that, so that's not my fault, but it is the published name of the thing. So now if it works out, people have to teach their students about Thor's hammer, and that's pretty funny. But this is just another increase of what it looks like graphically. That was really all I had. Thank you guys for listening. I know that it was somewhat dry at times, and I had a lot of numbers, but I really appreciate it. Do you guys have any questions or comments or concerns? Do you just want to talk about, like, the snow? Or? Yes, sir.
Most of the practical applications involve blood testing, similar types of situations.
Oh, I'm sorry. That was my fault. I got too excited to answer questions. If you could ask one more time for the people online.
Is most of the applications for what you do related to blood testing and biological analysis?
Yeah, for the moment it is. We've also used it to look at soil testing, but it is, we looked at soil testing in, before there was a mining operation to start. So we had to develop very, very low concentration standards to test about, and then had to make sure we could see what we were seeing. But primarily it is focused on the human body at this point. We are looking at, currently in our lab, we are looking at some protein compounds that are associated, at least in the literature, with ovarian cancer. So we were looking at a protein in hopes to test for ovarian cancer early, just perhaps in a routine blood screening, because unfortunately ovarian cancer is caught very late, normally when it's caught. So anything we can do to help that out. Yeah. Yes, sir.
I had read earlier about, somewhere in Scientific American, they talked about mass spectrometry being used to identify viruses, and I thought that was way too hard.
It is incredible. I've read using paper spray, EI ionization. It is literally incredible what they are doing. I also did not believe that mass spectrometers could accurately look at that high of a mass range. Normally they can only do, at most, 30,000 or 30K Daltons or whatever, and they're doing hundreds of. It's incredible. I don't know how they do it. I caught one of their posters at a conference one time. It was wild to me.
Yeah, I think they were using the time of delay, because like you just count how many milliseconds it takes from shooting the sample at a wall to how long it gets there, and you calculate how much energy, and then you figure out, like, okay, it took this long, therefore it was 30,000, and like, every virus weighs a different amount, but you haven't, but you're working more on proteins.
I am, yeah. Unfortunately, I'm not that interesting. That is very interesting. No, yeah, it is. They're doing great with the time of flight system. It is great because the thing that humans can measure the most accurately on the planet is time. Like if you need to do another base 10, they can always just put another base 10 of time on there as long as they have electronics fast enough to turn it off. But yeah, no. Yeah, I believe one of the undergrads at Duquesne when I was there left and went to grad school to work on that project. It's just great. That's my humble brag, as I know somebody who did a thing once. Yes, sir.
I used to work on a GCMS
Oh,
now 40 years ago, and we would be very happy if we got resolution
Yes.
of plus or minus one mass unit there up in the 400, 500, 600 range there.
Yeah.
What kind of precision are you getting for some of these, and how big are these molecules?
so you're right. With GC, you are going to, one mass unit is probably good. With triple quad, I think it's officially like 0.6 resolution. So like in theory, you can tell 101 from 102. So we actually, for our protein system, we're using a thermoofficial Astral, which has an Orbitrap in it. And I believe the resolution is like 10,000. Like you should, in theory, you can have 10,000 discrete points between 101 and 102. It doesn't ever work like that, but it is very interesting, and it does work very well. We were able to see some great things. But yeah, it all does depend on what type of mass spectrometer you're using. Sorry. Yes, sir.
Hi, we have a question from our online audience here. From Elise Stewart asks, well, first of all, a statement. Hello, I conducted my graduate research on the analysis of polyaromatic
Yeah.
hydrocarbons and
Okay.
PFAs with respect to various drinking water samples in southern PA.
Then she knows everything's terrifying.
Right. And I was curious if IDMS or SIDMS be applied to analyze trace amounts, ppm, of bulky organics like hydrocarbons or PFAS.
Yes, it is less useful for SIDMS because PFAS tends to stick around with what it is. It is unfortunately very resilient, but it is great. We are actually working on looking at one of the EPA suites of PFAS with it. I believe an undergrad was just looking at in dog food, PFAS in dog food. I don't know if that publication is coming along, but it is absolutely an IDMS way to look at it for very low concentrations. Yeah, I would recommend it. Other than, again, for any medical certainty, when you do have to run known EPA methods. Oh, yes, sir. Oh, wait.
And space-based mass spectrometers, such as you would find on lunar rovers, can they do quantitative analysis of detect the presence of either proteins or protein precursors?
I believe so. I certainly am not an expert in astral chemistry. It is fascinating as a study. I believe because they are in space, they have really good time of flight systems because it's just space. They don't have to worry about pumping down any vacuums. So I think they have very good time of flight systems, which are the ones primarily used for protein quantitation. So I would, well, again, I have not researched nearly enough of it. I would say that, yeah, probably. Yeah, sounds right. I know that they have been looking at it specifically for organic molecules that have come out of comets, or I think, right? Am I crazy? I might be crazy. But and I believe they were looking at proteins that had possibly been ejected from like moons, that volcanic moon that I do not remember the name of because I am not smart about space. Io, maybe, I don't know. Yeah. But yeah, I know that they do frequently use spectrometers in space, and that's how I would do it. But I'm sure the people at NASA are much smarter than me, so don't tell them how I would do it. Let them do it.
Any more questions from the audience? Here we go.
This is fun.
Do the mass spectrometers mostly work on the molecular and heavier level, or is there any interference from the quantum effects of the individual atoms?
So it's not, quantum effects are too, they don't really affect very much in a mass spectrometer. They are too light. The mass there is just, when we're looking at, I mean, at best, we might be able to see the mass of an electron, and quantum effects are much less than that. There are polyatomic effects that you have to worry about, where sometimes after the ionization, two atoms will come together, which I always thought was just a fascinating research topic to, instead of the collision cell in a mass spectrometer, if you used an addition cell, but then sprayed a different analyte to kind of see how two molecules would interact in the gas phase like that. I always did think it's funny that we study chemistry, but we study this weird aberrant form of chemistry that's on Earth, that's under standard temperature and pressure, and that's nowhere else in the universe. So much so that, like, really, if there is ever people on other planets, the chemistry would be different. It just would be necessarily. So I always wanted. I pitched that to my PI one time, but he didn't want us to drill holes in our mass spectrometer, so we didn't. But if you guys are trying to go to grad school and maybe pitch a thing to NSF, I think that's a good NSF grant. You'd have to do a way better job of describing it.
All right. If any last questions before we pack it up for this evening? Well, I'd like to thank you, Jeremiah, for coming out tonight. It was a really great pleasure to have you. I'd like a quick round of applause. I'd like to thank our online audience and our in-person audience for this Cafe Sci, and we'll see you next month.
Thanks so much, everyone. I really appreciate you coming out and hearing me talk.